yesterday. What is a stationary point? A stationary point is any point where the tangent is a horizontal line. That is where the derivative would be 0. Remember, we put stationary points on our number line. We also put critical points. Well, critical points include stationary points, but also include non-permissible values. So there are 3 types of stationary points. We have mainly dealt with maximum and minimum points, but I talked to you about an x cubed graph having what's called a stationary point of inflection. And we're going to find out later that an inflection point is where a graph changes from being, see how this part before x equals 0 is bent downwards, and this part after x equals 0 is bent upwards. The moment it switches from being concave down, we say, to concave up is called an inflection point. And it's another point on our graph that can help us graph things really nicely. So that is why it's called a stationary point of inflection. It's a stationary point because the tangent is flat, but it doesn't make a max or a min. So these are the 3 types of stationary points. This one has local min and local maximum. We call something a local min or a relative min if it's just the biggest or smallest in its little area. We call something an absolute maximum or an absolute minimum if it's the biggest overall. And here's a picture of our stationary point of inflection. It still is increasing the whole time, but I don't know if you notice here, this section was bent downwards, concave down. This one is concave up. So we get something called the first derivative test. And we've already been doing this without naming it. When we find our derivative, our first derivative, and we make our number lines for that first derivative, when we plug things in, we find out where our original graph was increasing and where our original graph was decreasing. And it is so obvious, what has to happen at 2? It has to be a local max. Because the only way you can increase and then decrease is if you have a maximum there. There's no other way you can do that, unless, of course, the 2 was a non-permissible value, right? So we're assuming that this is the place where the derivative is equal to 0. This is a stationary point, not a non-permissible value. Then that has to be a local max. This one, really obvious from this picture, that this has to be a local min. So when something asks you to use the first derivative test to prove something is a local max or a local min, you will need to show 2 things. Okay? To prove something is a local max or a local min, the 2 things you need to show is, 1, that the derivative at that point, in our case, I'll just use C, is equal to 0. That has to be, because otherwise it could be a non-permissible value. You could have increasing then decreasing and not have a maximum because that point's a non-permissible value. So you do have to show, no, it is a stationary point. My derivative is 0, it's a stationary point, and then second, I show either increasing to decreasing or vice versa. If you show this number line and show that it's increasing to decreasing, then you've shown the 2 things that make something, in that case, would be a maximum. If you show decreasing to increasing, you would prove it's a min. So this is called the first derivative test. And we've been doing it already. Okay? In other words, a local maximum is a point where the function changes from increasing to decreasing. I'm going to put a number 1 there, and the derivative is 0. I'm going to put a number 2 there to remind you that if you forget to say one of those things, you will always lose a mark for explaining. Okay? When something says, can you use the first derivative test to explain something? It's like, it happens so much that people just like, I'll just give you one reason. And then I'm like, oh, but it could have been a non-permissible value. You have to be more clear. So if you remind yourself that you always need 2 reasons, right? Changes from decreasing to increase and the derivative is 0, then you're fine. So there's always 2 reasons to show something is a max or a min. So here's an example. Find the stationary point of the function and show that it is a maximum using the first derivative test. So you know this is a parabola. You know this is a parabola that's going down. So you know that it's going to have a maximum. By using the first derivative test, you would find your derivative and then find where your derivative is equal to 0. Once you find that x value, that's telling you the x coordinate of your vertex of this parabola. In order to find the y coordinate of that vertex, you would have to take 5 over 2, plug it back into the original equation, and solve. Now we can make our number line for our derivative here, and plug 5 over 2 in it. And remember that we write f prime of x on this number line to remind us when we're choosing a value to plug in, we're plugging that value into our derivative. So for example, what's less than 5 over 2? I like to use 0. 0 usually makes mental math nice and easy. Plug in 0 into my equation, I would get 5. This section's always positive. Plug something bigger than 5 over 2, like 10. It's going to be obvious when I plug in 10 into my derivative. Negative 20 plus 5 is negative. This section is going down. And plugging in 5 over 2 into our original equation gives us negative 3 over 4. Now we know that is a maximum. In order to show that you understand, here's a picture. There it is. In order to show that you understand the first derivative test, we need to make a statement showing the 2 things. So here's number 1, right? Since it's positive before and negative after. And I used inequalities, you can use words. Since f prime of x is positive before x equals 5 over 2 and negative after x equals 5 over 2, that would be good. I didn't give my second reason, right? I also need to say, and, look at that, here I go and I spout out about how important it is to show 2 reasons, and then, and f prime at 5 over 2 equals 0, there's our second reason. We know that it is a maximum. We need to acknowledge that we see both of those things. And I think what is sometimes a challenge is a student does the work and they're like, well, I showed it in my work, Mr. JR. Doesn't that imply it? I guess the idea is in these explanation questions, they want to make sure that you really see it and understand it, so you explain it as well. So there's our 2 reasons. It's increasing before, decreasing after, and f prime at 5 over 2 is equal to 0. Therefore, it has to be a maximum. So we'll do another one. We'll see if I remembered both things in my explanation on this one. show that this one's a minimum. Okay? So we find our derivative. And you're going to find your derivatives in this chapter way easier than your derivatives. Like we went a little crazy in chapter 2 how complicated our derivatives were. Then for applications, we go back to easier ones. Next, set it equal to 0. X would have to be 2. Draw our number line. And if you plug numbers into your number line, you will find it goes from decreasing to increasing. We can plug 2 back into our original equation, and we find out that the point is 2, negative 3. So our statement here. Since, oh no, I did this time I did. Oh, I missed. Here, since f prime of 2 is 0, 1 and 2. Since f prime is negative before x equals 2 and positive after x equals 2. Right, so I'm going to write about here. If you would prefer to use the words negative and positive, that is perfectly fine. We know it has to be a local minimum. So the explanation is there, but I actually find the explanation does nothing compared to this little diagram. Doesn't that diagram just scream minimum? When you like draw those arrows on that number line, it's like so obvious it's a minimum from there. You feel like I shouldn't have to write anything. I kind of agree. This is the best visual of what's happening. Writing it in words doesn't show it as well, but we do need to practice explaining it in words as well. At the bottom there's a little explanation. You can find, if you have a graphing calculator, you can find maximums or minimums on your graphing calculator. If you don't have a graphing calculator, there's a very good app on your phone called Desmos. You can graph an equation. And since a max or min is really important here, here. Y equals 2x squared plus 5x There we go. So there I've written an equation. The graph is automatically there, and the point, you just have to click on it when you see it to find the max or min. Probably better than your graphing calculator that way for how easy it is to find a max or min. So, Desmos, a wonderful app. Oh.